Let us try to recollect what we did yesterday through this model. This is 1/200 scaled model of this 3, name is the CAD. It is operated by Lufthansa. So, this is just one of the aircraft models, and let us try to understand the nomenclature that we discussed yesterday. So, this part of the aircraft which is used to carry the passengers and the freight is called fuselage. Wings are these two surfaces. There is a twin engined propeller aircraft. So, you see 2 engines symmetrically located with respect to a plane that will discuss about. This surface is called vertical tail and this surface is the horizontal tail. So, we defined access system. If you remember yesterday we defined an access system to the aircraft. X, Y and Z fixed at the with the origin fixed at the center of gravity or the center of mass of the aircraft. So, this X axis can be taken as the line joining the center of the fuselage cross sections. So, if you take the fuselage cross section, there will be a center for that, and when you join the center of the fuselage along its length, you can define this x axis at that line, or if the CG of the aircraft is not lying along that line, then we have to define this x axis differently. So, this x axis has to pass through the center of gravity or the center of mass of the aircraft. The aircraft is actually symmetric about this axis, about this plane which is passing through the axis x of the aircraft. So, if you look at this aircraft model carefully, this is the line or this is the plane which is dividing the aircraft into 2 equal parts, and that plane is the plane of symmetry, also called longitudinal plane of the aircraft. In that plane, this z axis is defined as perpendicular to the x axis. Y axis completes the orthogonal coordinate system. So, y axis is perpendicular to x and z axis. Okay. So, the motion of aircraft along the x axis in the forward direction was associated with the variable u, that was the velocity of aircraft along its own x axis. The side velocity is along the y axis, which is along the span of the wing, and if you look at this system, the right handed system tells us that if this is the x axis, the y axis is away from me along this part of the wing, and the z axis is downward. So, side velocity v is along the y axis of the aircraft. So, it is like this. And the downward velocity w is along the z axis, which is perpendicular to the x and the y plane. So, it is like this. So, this is this gives you 3 translational degree of freedom of the aircraft. Talking about 3 rotational degree of freedom, the roll motion of aircraft is defined along the x axis that we talked about, x axis of the aircraft, and it is like this. So, this is the roll motion, and the associated variable with this roll motion is the roll rate, which we talked about yesterday. So, this roll, a positive roll is right to me this wing going down and the left wing going up. The pitching motion is about the y axis, which is this axis, and is in the xz plane. So, aircraft pitching up means positive pitching motion, and that is going like this. So, aircraft is rotating about CG in this fashion if we have positive pitching. And the associated variable is the pitch rate q. The other motion is the motion, rotational motion about the z axis of aircraft, and this motion is called yaw. So, the wing to the left to me is going forward, and this wing to my right is coming towards me. So, this is called a positive yaw motion, and the associated variable to that is r. Okay. So, should you really wonder where and why these surfaces are located on the aircraft in this fashion? So, for example, if you look at this wing is lying low on the fuselage. This the engines are lying in front of the tail and on the wing. We could also have location of engine somewhere else. We could also have one engine, for example. So, here we see 2 engines. If you look at the vertical tail, it's looking up, vertically up. Why is not upside down? That is also one might wonder about. And the horizontal tails. So, tails are called tails because they are lying behind the wing, but there are surfaces which are also like tails, but they lie in front of the wing, and those are called forward tails. So, if you remember, canard is a control surface which can be called a forward tail. Okay, so what I was explaining is you would wonder why these surfaces on the aircraft are located in the way they are located. This wing could have been actually straight, no, not tapered like this here. It could be lying on top of the fuselage, it could be lying midway, and look at the location of the horizontal tail. Horizontal tail is lying above the wing. What are the regions for all these things, no, to come to such a design? That is what is the subject of study of flight dynamics course. So, after explaining all that, let us look at how wing is actually. So, let us try to understand some of the basic aerodynamic surfaces of basic aerodynamics of aircraft, let us say. So, aircraft is actually consisting of lot of aerodynamic surfaces here, of which you can see this wing, you can see the tail is also aerodynamic surface, vertical tail and the horizontal tail. So, let us look at the section of this wing. If you take the section of this wing, the way it looks like is this. This shape is called airfoil. Airfoil will constitute the wing. So, any section along the y axis of the aircraft, so parallel to the x z plane will give you this section, and this is what actually is resulting in giving you lift in flight when air is flowing over this surface. So, let us try to understand some of the basic features of this airfoil, and that which will help us defining some parameters later on. So, this airfoil as it looks like, let us go back one step further, and let us talk about an airfoil shape which is so much of this can be covered in the aerodynamics course, and we assume here that you have seen what I am going to talk about. So, this airfoil which looks symmetric about this line is called a symmetric airfoil. So, this part above this line is a mirror image of the part which is lying below this line, and this line is called the chord line. This length joining the leading edge of the airfoil and the trailing edge is given by this distance, which is the chord length of this airfoil. So, this airfoil is symmetric, and what it means is, if the relative wind is coming along the chord line of this airfoil, then the angle of attack which is measured with respect to this chord line is 0. when you change the orientation of this airfoil, so you can rotate this airfoil, and if this is the direction of velocity, then the angle of attack will change. So, for example, if this is rotated, the whole airfoil is rotated like this, then the angle of attack is this. The chord line for this airfoil, when it is rotated like this, is this line, which is making an angle with the velocity vector, which is giving you the angle of attack, which is positive. And this gives you a lift over the airfoil, which is symmetric in this case, okay, and the profile or the lift curve for this section, which is denoted by this small CL against angle of attack, looks something like this, passing through this 0 origin of the CL versus alpha, this axis. So, it is not possible that no, throughout you keep changing this angle of attack and you keep getting no increase in lift. At some point, what happens is flow over the airfoils starts separating towards the leading edge at some point, because of which there is a loss of lift. So, instead of creating lift, starts the lift actually starts falling down, and that is because of the pressure distribution over the top and the bottom surfaces. So, there is a range of alpha within which you can keep getting increase in lift because of the relative wind coming onto the airfoil. Beyond this alpha, which is called alpha stall, flow separates over this airfoil and there is a drop in lift. So, this region where you see almost linear variation of CL with respect to alpha is called pre-stall region, and beyond this alpha stall you have post stall region. So, in order to derive maximum efficiency from our wing in terms of producing lift, what we would want to do in normal flights is to fly in this pre-stall region, where we can keep changing angle of attack and then keep getting an increase in lift. So, this is for this symmetric airfoil. Now, let us look at another airfoil which is not symmetric. This is one such airfoil which is not symmetric, and the major advantage of using such airfoil is to produce lift even at 0 angle of attack. So, let us see what happens here. So, we have this airfoil which is bulging on the top side, and flattened on the bottom side, and this is the chord length which is joining the leading edge and the trailing edge of the airfoil. We can define another curve which is joining the center of each section of this airfoil. This line is called in this case, in the symmetric airfoil case, the mean camber line is same as the chord line. So, here the mean camber line is slightly away from the chord line, and so if this is the case, when the mean camber line is lying above the chord line, we say that it is a positive camber. So, let us look at what happens in this case when we have a let us say velocity vector aligned along this line. Now, because the chord line, so it is a similar case if you want to represent here, then what you need to do is you need to define this line parallel to the velocity relative wind vector. So, if you want to draw parallel between the two airfoils, then let us say this is the velocity vector of the relative wind, and the airfoil is a positively cambered airfoil now. So, what is happening in this case? So, this is one such airfoil. The chord line is joining the leading and the trailing edge. So, what you are seeing here, by giving a camber to your symmetric airfoil, an increase in angle of attack. So, for the same velocity relative wind speed, but for a different camber of the airfoil, you see there is an angle of attack associated with it, and what it results in is giving you a positive lift at positive lift at 0 angle of attack, which is this. So, in a similar fashion, we can invert this airfoil, and then the airfoil becomes a negatively cambered airfoil, and in that case alpha becomes negative, alpha or okay. So, at 0 angle of attack, what you get is a negative lift in the case of negatively cambered. So, clearly if we want to fly our aircraft at alpha which is as low as 0 degree, then we would prefer the positively cambered airfoil over the other two cases, because it gives me the higher lift coefficient. So, CL is here so you can see clearly increase in the maximum CL that you can get in the three cases. So, maximum CL is at alpha stall. Okay. So, where all these things coming into picture, let us look at that. So, lift is lift over the wing, total lift by the total lift generated by the aerodynamic surfaces of the airplane is is going to be depending upon the airfoil that you choose. So, in case you have chosen this positively cambered airfoil for the wing, that is going to give you much higher lift as compared to the other two airfoil. So, this is clearly depending upon the choice of airfoil. Choice of airfoil is also depending upon the regimes of flight that you want to fly. So, let us look at some of the flight regimes based on speeds. If you talk about Mach number, which is the ratio of the speed of the airflow over the speed of sound, and speed of sound is a function of the temperature. So, if you talk about this 0 to 0.5 is, if you want to operate your aircraft only in this flight regime, then the choice of airfoil should be different, because the flow in that case is incompressible. Regime of flight between 0.5 Mach number and 0.8 is compressible. So, flow over airfoil in this case is compressible in this speed regime. Mach number above 0.8 and below 1.2 is transonic region, where the wing can encounter some of the discontinuities in the airflow because of presence of shock, weak or strong, depending upon the speed, which whether it is close to 0.8 or close to 1.2. So, there are a lot of discontinuity in the flow taking place in this region of speed. this is the supersonic regime of speed. So, Mach number here is greater than 1.2 and less than 5. Clearly here there are phenomena associated with shock formation taking place. So, in front of the the wing or any other surface which is looking like a wing, there will be a shock formed, and because of the shock formed in front of the wing, there will be a discontinuity in the flow. So, depending upon what regime of speed we intend to fly for a longer duration. So, if you look at the typical flight profile, you have to start with low speed to take off, and then attain the height at which you want to fly your aircraft, and then increase your speed to the speed regime in which you want to fly your aircraft. And the third phase is landing. If you do not want to talk about some low speed maneuvers, for example level turn and so on. So, these are the flight regimes that one can design the aircraft to fly in depending upon the requirements, and the choice of airfoil or the wing section is going to dependent upon the speed regimes. All right. Okay. So, that is why we said in the last in the first class that the forces, the aerodynamic forces, or if I want to just write F for all aerodynamic forces, it is going to be a function of angle of attack, side slip angle, and the Mach number. Okay. If you want to include also the compressibility factor with the Mach number, then you are talking about what is called Reynolds number. Reynolds number is defined as the density into the speed into L, which is a characteristic length. In the case of airfoil, this L could be taken as the mean aerodynamic chord, and the viscosity of the fluid. So, you can also write this as mu is the viscosity of the medium, and mu over rho is the kinematic So, in general these forces are also going to be functions of the rates and in rate of change of these angles. And similarly moments are also going to be functions of these variables. So, if you want to look at how Reynolds number is having an effect on the CL, this lift coefficient of the airfoil with respect to also the thickness of the airfoil, we can quickly have a look at that. On the x axis we have you want to look at how CL max is varying with Reynolds number and the thickness to chord ratio, which is in percentage. So, thickness of the airfoil is actually the maximum thickness. So, wherever you find the maximum distance between the top surface and the bottom surface, that can be taken as the maximum thickness of the airfoil. If we plot or the thickness, thickness or the maximum thickness are the same. So, let us try to plot the CL max versus the thickness of the aircraft in terms of the percentage of the chord and the effect of the Reynolds number on this CL max. So, clearly if you increase the speed of flow over the airfoil, then you will get more lift, and this one is for the highest Reynolds number, which is nine into 10⁶, and it falls down. CL max falls down with respect to this Reynolds number. So, if you decrease the Reynolds number by so decrease by 1/3, and you see a decrease in the CL max. So, at different values of this T by C ratio in terms of percentage, you see a fall in CL max with respect to the speed that you are flying at. So, clearly there is a T which is giving us the CL max in different speed of flow over the airfoil. So, we have chosen some airfoil depending upon our need, and so we are getting lift. So, major contribution coming to the lift is from the wing. Let us say we have decided on an airfoil for the wing. Now, after deciding that, the wing is formed, and now what we want to do is we want to change this lift. So, there will be a lift corresponding to each angle of attack because of the airfoil that we have chosen. Now, what we want to do is we want to increase the lift in flight. When you are changing the flight speed regimes or the angle of attack, what you want to do is you want to increase the lift or decrease the drag, or both. So, in case you want to change the lift, drag profile, or both together, of course, both of them are going to change together because of the flow field changing over the wing due to the change that we are looking at now. So, they are leading edge or trailing edge flaps mounted on wings which can further change the aerodynamic forces in flight. So, if the CL versus alpha curve is looking like this, it can be. So, this for symmetric airfoil we can go back and assume that the wing is made of positively cambered airfoil, and let us say we get this kind of CL versus alpha profile. In flight, this profile can be changed using the trailing edge and the leading edge flaps, which are normally mounted on high performance aircraft, to not only change the maximum lift coefficient, which is now this, previously it was here, but also to change the alpha stall. So, use of trailing edge and leading edge flaps are now very common on higher performance aircraft. Some of the examples of these flaps are so this kind of arrangement is called, there is a thin curved surface which is lying in front of the leading edge of the wing, is called leading edge slat. There is another thing wherein the leading edge of the airfoil can be given a droop in flight. So, this is called this kind of arrangement is called leading edge droop. This is called Kruger flap. So, these devices are used on high performance aircraft nowadays to change the lift profile in flight. Let us also define what is known as aerodynamic center and airfoil. So, if you look at the pressure distribution, over the top and the bottom surfaces of airfoil, So, that is what is giving us the lift, resulting pressure distribution, the resulting load due to the pressure is what is giving us the lift. And if the this load coming because of the pressure on the top surface and the bottom surface, they are not lying on the same point, then they are going to give rise to a moment, right. So, if the pressure distribution over the top surface of the bottom surface of the airfoil are such that the resultant load is not loads are not loads from the top and the bottom surfaces are not acting at the same point on the airfoil, they are going to form a couple resulting in pitching moment. So, let us say the resultant loads are acting at two different points, then this kind of arrangement of the resultant loads are going to give rise to a pitching moment. There is one point on the airfoil along the chord of the airfoil where the change in pitching moment with respect to change in angle of attack is 0, and that point on the airfoil is called the aerodynamic center of the airfoil. So, the point along the length of the point along the length of the airfoil on the chord line where dCm over d alpha is 0, is called the aerodynamic center. So, usually for a symmetric airfoil, the aerodynamic center is at the quarter chord length of the airfoil. The quarter. Okay, so for symmetric airfoil, the aerodynamic center is lying at the quarter chord length from the leading edge, right. So, for symmetric airfoil, the the aerodynamic center is also the point where the resultant load on the top and the bottom surface is acting, and that gives me Cm quarter chord. So, if that is the case, we can also say that Cm C by 4 for the symmetric airfoil is 0. So, what it means is, in the case of symmetric airfoil, the aerodynamic loads are acting at the quarter chord length. So, there is no moment created because of the loads. So, Cm C over 4 is 0, and dCm C by 4 is also 0. Okay. In case of cambered airfoil, which is so, in case of cambered airfoil, the loads coming from the aerodynamics are not acting at the same point, and they are giving rise to a moment about the quarter chord, which is not zero. So, Cm at the quarter chord is not 0. So, you get a pitching moment, and this is actually equal to pi over 4 into some parameter which is not depending upon. So, this parameter depends upon the geometry of the airfoil alone, and is independent of the angle of attack. So, this being a constant and independent of angle of attack, dCm C by 4 for any airfoil which is a cambered airfoil is 0. So, what it means is the quarter chord of the airfoil in all three cases can be taken as the aerodynamic center of an airfoil, and this will have some implications which we will see later on. So, dCm over Cm at the quarter chord length for the cambered airfoil is not equal to 0. For positively cambered airfoil, this Cm C by 4 is actually a negative number for we can just